So the next talk will be Professor Ehud Altman from UC Berkeley. He will tell us about probing the effect of many measurements without post-selection. Ehud, please feel free to share your screen and start whenever you're ready.
Thank you very much. Yeah, thank you. I'll try to share my screen now. I think it worked. Let me just start the... Yeah, so I'll talk about something completely different. Hopefully not silly. I'll talk about measurement-induced collective phenomena in many body systems, and especially how to overcome, or at least go in the direction of overcoming a big fundamental problem in those, called the post-selection problem. And this is mainly based on very recent work with Sam Garrett, and also some previous work together with Sam and two students in Berkeley, Zach and Rohit. Just as by way of introduction, I want to talk about problem that basically in which measurements play a completely different role than in usual experiments that we're usually see in quantum mechanics. In traditional experiments, measurements are used as a diagnostic of a quantum state. So they're not really changing, or if they're changing the state of the system, we're not looking at this. We're actually interested in probing the pristine states using the measurements. However, monitored systems are systems where have non-destructive measurements in them, in the sense that after doing the measurement, the system is still intact, although it changes the state of the system. So the measurements have a non-trivial impact on the quantum state by making basically a quantum state collapse due to the measurement. And basically in such experiments, every time we do a measurement, we basically are deciding on which branch or trajectory the wave function will go. And at the end of each run of the experiment, we end up with a wave function that essentially we can't really reconstruct again if we have many measurements along the way, because that would be exponentially rare. So and the interesting things about these monitored systems are if we actually have access to these individual trajectories, and then we can see that the measurements in quantum mechanics actually have a non-local impact on the wave function. So the interesting new collective phenomena that we want to see actually rely on having access to these individual trajectories. On the other hand, as I mentioned, to get access to those is very hard, because to get a particular trajectory is exponentially rare. So the question I'm going to mainly talk about in this talk is how to overcome this conundrum. Just to demonstrate how measurements can have a non-local effect, here is a really, really simple system with three parties. I should have had letters here. Let's say this is A, here in the middle is M, and this is B, say Alice, Bob, and in the middle, M. A could be in, Alice could be in the Earth, M could be on Mars, and the third system B on Jupiter. And you see that in this case, Alice and M share a bell pair, and also M and Bob shall share a bell pair. Now let M measure her two particles in a bell basis. After measuring, it projects the quantum state on one of the bell states in M's lab. Let's denote it by little m. So it projected it into a Bell state, but that automatically projected also the wave function of the two particles held by A and B also into a Bell state. So we've created, by measuring locally in Mars, we've created a non-local state, a non-local correlation between Earth and Jupiter that did not exist before the measurement. So the measurement had a very non-local effect, and the resource on which this non-local effect was built was the entanglement in the original state. Again, in order to detect this non-local effect of the measurement, we have to have access to the measurement outcomes and then probe the particular state, the particular trajectory that occurred due to in one run of the experiment, right? In this case, there is only one measurement, so the post-selection problem is not very hard. But in order to detect this correlation, we actually need to post-select. Okay, so in this talk, I'll be interested in observing these non-local effects in many body states and seeing kind of universal collective phenomena induced by measurements. And there, of course, we need to make many measurements, and the post-selection problem is then becoming exponentially hard. It's exponentially rare to create the same state more than one time. And we're interested in the question, how can we diagnose post-measurement states if we can see each state only once? If we can get each state only once, we are not really observing them yet. So in the first part, I'll describe a very simple many-body setting in which such measurement-induced phenomena that are in some sense collective and universal can occur, and they're kind of simple. It's when we apply measurements to a quantum ground state. A quantum ground state is, in the first place, entangled at all scales. It has power law correlations, as we know. And now the question is, if I make local measurements in individual qubits, but leave a fraction of the qubits unmeasured, how do the measurements affect the correlations of the unmeasured degrees of freedom? That's the question. And we'll see that there could be a very interesting non-local effect of the measurements. And again, the question is how to observe it. I'll show one direction for observing it using a cross correlation between the measurements between measurements we do on the quantum system and some classical simulation. Then I'll talk about another problem. So in a sense, the first problem will, the first idea will partially solve our problem. We'll be able to see some effects, non-local effects of the measurement. However, the observations we'll get are going to be model dependent. They'll depend on the model in which we, a classical model for our system. In the second part, I'll talk about observing the measurement-induced transition in quantum circuits, where the observable order parameters of the transition are information quantities. So I'll show how we can generalize the idea of quantum classical cross correlations to quantum information quantities. And in this case, also, we're able to find both an upper and lower, we can both get a lower and upper bound to intrinsic model-independent quantities in terms of quantities that are easy to obtain without any post-selection. So that will be the second part. So let me start with the simple problem. It's very easy to set up the problem. Let's say someone gave you a ground state with power law correlations with entanglement on all scales. So you have a quantum ground state. I represent it as a tensor, and now we measure some of the degrees of freedom. After measuring, there is no dynamics. We immediately evaluate some correlations of another probe operator, let's say Z. It could be the same operator as local operator as the one that we're measuring, or it could be different. It really doesn't matter. In any case, we're measuring degrees of freedom that we haven't measured before. So they commute with the original measurement. So these are the preparation measurements, let's call them. And what happened here? Oh, yeah. So there are preparation measurements that prepare our state psi m, and then there are measurements of probe operators z that we evaluate their correlation functions. And notice that we want to look at the correlation functions in individual states that conditioned on the measurement outcomes m. So just to understand the gist of the problem, it's let's look at an example, which is the critical transverse field Ising model. It's a really nice example because it has a simple critical state in all dimensions. In this case, I draw the critical state, just a representation of the critical state in 2 spatial dimensions as a tensor. And as we know, we can understand, we can look before doing any measurement. The pre-measurement state is described by an effective classical partition function in 1 dimension higher, where tau is the imaginary time, and the correlations in the ground state are basically correlations in a single time slice of this quantum field theory. Right? This is the usual way we'll describe correlations in a ground state. No measurements yet. Now, suppose we do some measurements, then this picture doesn't change much. The way it changes really, it doesn't seem to change much, but there is a really important change actually. The important change is that the measurements show up in this time slice, tau equals 0. We now have to constrain some of the degrees of freedom to be exactly have exactly the measured values, so they can't fluctuate freely anymore, but basically have to be pinned to a particular value. So, but in a sense, in the quantum field theory, what the measurements have done is they've created some kind of defect, a 2-dimensional defect in a 3-dimensional problem in this case, or a 1-dimensional lower defect more generally, where we pin the measurement outcomes. And so in this way, we can essentially convert this problem of the post-measurement correlations to correlations on the defect surface, the defect that's created. Just by way of example, let's continue with this Ising model, and let's say we're measuring, to prepare the state, we're measuring Z order parameter, the order parameter at sites I, and then we're interested in how it impacts the order parameter correlations. And as we'll see in a minute, it's important to look at this, it's also important to subtract the disconnected part of the correlation function. So in this case, if we start from the simplest case of 3-dimensional Ising model, 3 spatial dimensions, then this is described by a Gaussian fixed point. And kind of let me skip over the details. You can do the analysis very simply in this case, just by analyzing scaling dimensions. You see that before doing the measurements, the correlation functions go like 1 over x squared, and it simply comes from the scaling dimension of the order parameter in the Ising field theory. That gives you immediately that the correlations decay like this. You can also evaluate the scaling dimension of the defect that you create by measurements, and immediately you see that it has that it's relevant under RG. So what it does, it essentially creates a pinning surface where the order parameter is completely pinned. It created a boundary where there was no boundary before the measurement. So no matter how dilute the measurements are, they'll flow to strong coupling and create strong boundary. And now calculating these correlation functions is like calculating boundary correlation functions instead of bulk correlation functions. And it's one can show that these actually have another have a lower scaling dimension. They're more irrelevant operators, boundary operators, because they have another time derivative associated with them, and it changes the correlations from 1 over x squared to 1 over x to the 4th power. So this is really an example that you can solve from the beginning to the end very easily. and shows you that making just local measurements on a quantum state can completely alter the correlations at arbitrarily long distances. That's, if it was unitary dynamics, this couldn't have happened because of Lieb-Robinson bounds, but measurements could immediately change the correlations at arbitrarily long length scales. So this is the example, but again, there is a significant obstruction into seeing how these correlations change. So to understand this obstruction, let me kind of go back to the post-selection problem and understand what we're doing here exactly and why there is a problem. So here is the schematic representation of the quantum state at the top psi. And now we are measuring the operator Z on many sites to prepare the state. These are these red sites that now show definite spin. And we basically have projected the state psi onto a new state psi m that depends on the values of these measured spins. Now, to characterize this measured state psi m, we measure a probe observable x, for example, and every time we run the measurement, we're of course not measuring the expectation value of x, we're getting some outcome of x, let's say xm, 0 or 1, or -1 plus 1. So of course, just by looking at the state once, we're not getting the expectation value of xm, because in order to obtain the expectation value of this observable x, we need to obtain the same state psi m many times and average the result, right? We can't do that because we can get the state only once. So we can ask, okay, maybe we just want to average over measurement outcomes, but you can now see that if I want to basically naively average over runs of the experiment, the outcomes I get x here, it'll be basically the same as averaging over measurement outcomes PM, expectation value of x, and I can reorder the psi m's and see that basically this is the average of x in the average, the trace of x in the average density matrix, where the average density matrix is simply a sum over all trajectories acting on the density matrix, all the possible measurement projections acting on the density matrix. But the measurements basically create a complete local quantum channel, and a local quantum channel can't have a non-local effect. So there cannot be any interesting non-local effect. We can't detect any non-local effect by looking at the linear average of x, linear in the density matrix row. What we need actually is something that's non-linear in the density matrix. The simplest one is the fluctuation of x between trajectories, right? This is the variance. So this kind of variance, especially the second part, right, is nonlinear in the density matrix. If we only had the first part, this would be easy to average, but the second part is already impossible to get in experiments, again, because every time we do the experiment, we need to know what is the expectation value in order to square it, but we don't get an expectation value for a single run of the experiment. So how do we get around that? Is there any question so far? So our goal is to get around this. So here is the first idea to get around this. How do we observe unobservables like this? So what we want is to look at the average over measurement outcomes of x, expectation value of x in the measured state squared, right? That's what we want. And as I mentioned, this is something we can't get. So let's try to get an alternative quantity that does correspond to a linear average. So you don't really need to know in the first place the expectation value in this state, right? So in this case, so let's do the following. Let's, instead of measuring, evaluating the average of x, let's evaluate the average of x reweighted by some number w that depends on the measurement outcomes of every run of the experiment. Every run we get a different measurement outcome labeled by m, and suppose we can calculate a number somehow that depends on the measurement outcomes. If that number was just a constant independent of the measurement outcome, we'll go back to the previous slide where we're really looking at average, a linear average with the average density matrix that's trivial. That basically corresponds to a quantum channel. So the natural choice for what is the natural choice for W? We have enormous freedom in choosing W. A very nice natural choice is if we had some classical model that, given the outcomes of the measurements M, could calculate an estimate of the expectation value of X in psi M. It's just an estimate, and we call it expectation value, the classical expectation value, because it's using some classical model to calculate this. So if we write it like this, what we really are, so we can easily get this, this quantity by basically averaging over runs, usual Monte Carlo average over runs. Every run we get a set of measurement outcomes M. Using them, we calculate XC of M, and we also get the outcomes of the probe operator XM, which are just numbers 0 or 1, basically just the eigenvalues. But averaging this, just Monte Carlo averaging over runs, gives us this quantum classical cross correlation. We can also compare it to the fully theoretical result without needing any experiment, really, which is just the classical expectation value squared average over measurement outcomes. This doesn't require the quantum device at all. So we can compare these two things. And in doing so, we actually already solved some fundamental problem. You can ask me, well, how do I know that the classical model is good for this system? Can I actually even calculate this system efficiently and so on? So what I'm going to say, I'm going to find some classical approximation that I can calculate efficiently. And now I at least can evaluate how good it is. Because in usual experiments, when we compare theory to experiment, we have a very standard way of doing this. The experiment, the output of the experiment is an expectation value of some observable X, and this is here in the blue dots here. And the classical calculation, our classical model can also output the same kind of expectation value, and we can compare them one to another. In these monitored systems, we don't even have the starting point because we can't extract any expectation value from the machine, right? Because it's conditioned on measurement outcomes, we can't get any conditional expectation value because every time we get a different state. So we can't even start with this comparison. So the quantum classical correlations I gave here are the next best thing for the experimental data, right? We can get experimental data, which still depends somewhat on the classical model for calculating this XC, but we can compare this quantum classical correlation to something that's completely extracted from the classical model, and that will at least evaluate how good our classical simulation is. We're still not completely there because we are not learning anything model independent about our system yet. We are learning whether our classical system, how good our classical system is in simulating our system, but neither of these quantities, the classical quantum or the classical is completely independent of the model. So can we learn something model independent from experiments? That's the next question. So how much time do I have?
About 0 minutes, but you can continue for, say, like 2 minutes.
Okay. So very quickly, I'm going to apply this scheme to measure information properties in the measurement-induced and see if I can see the measurement-induced phase transition. So I won't go over the in detail. It's just a random circuit where I have random unitary gates and measurements dispersed with some probability P. And it was shown that in this case, as a function of the measurement probability, there is a phase transition at the critical measurement probability where the entanglement entropy of the output state is becomes area law. If you're measuring not frequently enough below PC, your output state has volume law entropy. And again, you have to evaluate the entanglement entropy of half the system in the state conditioned on the measurement outcome. So it's and then average after the fact. Or you can look at another correlation, which would be more interesting for us, more useful for us, which is take the same circuit, measure everything at the end, except for two distant qubits, 1 and 2, and look at the mutual information between these two distant qubits conditioned on the measurement outcomes M. And we'll find that this corresponds in an effective StatMech model. It corresponds to just the order parameter correlations. In the volume law phase, these would be entangled. That reflects the long-range entanglement in this volume law state, and it's just entanglement between these two remaining qubits. And while in the area law, the entanglement entropy between them, or the mutual information between them, will decay exponentially with the distance between these two unmeasured qubits. And at the critical point, this entanglement decays as a power law of the distance between them. So how do we measure entanglement entropy of, say, qubit 1 or qubit 2? That's conditioned on measurement outcomes. So let's try to apply the quantum classical cross correlations for that. The entanglement entropy of the density matrix of a single qubit, let's say rho m here, this single qubit we're interested in, is traced around rho m log rho m. So the idea is to replace log rho m with a classical estimate log rho c of m that depends on the measurement outcomes that we get from the experiment. The problem is, what do we replace rho m with? Because we don't have a classical, we don't have a snapshot, we don't have a measurement outcome that corresponds exactly to the density matrix. So in this case, we have, but we do have one thing that actually corresponds to something like a measurement, single shot measurement outcome. We can construct what is called the shadow of this density matrix by measuring that qubit in a random basis defined by the local unitary operator U acting on that single qubit. And we construct, this is well known from this shadow technique, to construct this density matrix, which basically is, this shadow density matrix is a silly density matrix because it's not even positive, but it has the nice property that the mean over U, the average over U, basically converges to the density matrix rho m. Now we have, if we take this, we now have a linear average. We can change the, because everything is linear, we can change the order of the measurement average and the unit average over unitaries. And we see that this object that we can simply average, Monte Carlo average over runs of the experiment, really converges into this object that to this object, which is the quantum classical estimate of the entanglement entropy of the qubit. And the punchline is that this is a really interesting quantity, because if we look at the difference between it and what we really want, which is the entropy of the entanglement, von Neumann entanglement entropy, it's the relative entropy, quantum relative entropy between them is always positive, and therefore we have an upper bound, rigorous upper bound to the quantity, the intrinsic quantity we're after. I don't have time to explain, but we can actually even get a lower bound to the quantity we're after. So we can, by using only post-selection free quantities, we can both upper and lower bound the entropy we're interested in, and in this way get, maybe even have a variational way to improve our classical model and describe the measurement-induced phase transition. Okay, so
yeah,
this
great.
is
It'd be good to end now. Yeah.
So this is the last slide, basically last two slides. This is an example where we actually apply it to the measurement-induced phase transition in a very small system, because we don't have the quantum system to calculate, to generate the quantum part of the quantum classical correlation. So we use an exact simulation, which is, of course, not scalable, but in principle, if we had a quantum device to do it, that would be scalable and we would be able to do it on large system sizes. The classical model here is a matrix product state calculation with increasing bond dimension. And you see that in this case, we have a different, we have both a lower and upper bound that hug the exact result that we're after. And at least at the critical point, we can show that we can, with polynomial effort, that we can characterize with a critical power law, approach the using this quantum classical correlation with matrix product state classical model for calculating these correlations. We can approach the critical point and show and get the critical behavior with polynomial effort only. So this is a summary. I just want to give one slide on the outlook. I think really interesting direction that I want to put forward is that because this quantum classical cross correlation is an upper bound to the real entanglement entropy we're looking for, even if we don't have a good model, for example, in one dimension, we have a good matrix product state model to calculate the classical part. But let's say we're doing a two-dimensional plus time calculation. We don't have a good model. We can we can run an experiment on one side, output the measurement outcomes, and give it to some big neural network model that will output the classical estimate for the classical estimate for the density matrix, and using both the quantum shadow and the result of the classical model, will evaluate this quantum classical cross correlation, quantum classical entropy. And that will be the objective function will be to minimize the relative, to minimize that object, right? It just wants to minimize this object. It will train the neural network to do that. So we can train the neural network, a machine, to solve or to give a better classical simulation than we know how to do now using, so in essence, the quantum device will train our classical system. So basically, this is it. Sorry for going a bit over time.
Okay, great. Thanks, Ehud, for the great talk. So before inviting for one quick question, let me just say that there will be a 15-minute free discussion time when people can feel free to ask questions to both speakers or just freely discuss, and it will be all recorded. So don't leave the Zoom meeting too soon. All right. So any quick question for Ehud? Do you want to comment on like which systems allow for good classical simulations?
Well, so first of all, we know we can do a good classical simulation if we have a stabilizer circuit. So all the measurements and all the unitaries are basically keeping the state a stabilizer state, the Clifford circuit. That will allow an exact calculation. In 1D, in principle, we expect matrix product states to work well in the area law phase, as long as the entanglement is area law, and not work well in the volume law phase. And what I showed here is that they work well probably also at the critical point. Not surprisingly, sort of like we expect in the ground state, except here we don't have a theory for the ground state. So classical simulations should work in terms using matrix product states should work in one dimension. But I think although we don't have, strictly speaking, a general way of calculating in two dimensions, if we think about the information theoretical meaning of the measurement-induced transition, that if we're in the area law phase, it's easy to learn the state of the system, while it's hard to learn the state of the system from the measurements in the volume law phase. We expect to be able to simulate this, at least within the area law phase. We expect to have a good simulation, to be able to do a good simulation, but I don't know if we have a general understanding of how to do it. What I want to propose is maybe there is a way to use machine learning, because now I have a good objective function that I know should be minimized. It basically turns it into a variational problem, right? It's a variational problem without a Hamiltonian or a ground state. Now we have a new kind of statistical mechanical variational problem that we can try to improve our classical models using machine learning, using large neural networks.
Great, thanks. So let me stop the recording now, and we will do the